Next, I want to talk about functions, and functions are special types of equations or special types of graphs. So if an equation in two variables yields precisely one value of y for each value of x, then we say that y is a function of x. So for instance, let's say you had an example, right? So I'm just going to make this up. Let's say when x equals 0, you got the answer y equals 1. When x equals 1, you got the answer y equals 4. When x equals 2, you got the answer y equals 3, and so on. Notice that for each x value, you're only getting one output. That's a function. Something that's not a function would be like this. Let's say you have x equals 0, and you got both y equals 1 and y equals 6. This is not a function, okay? So with a function, each x value is only paired with one y value, whereas when you do not have a function, a single x value can give you different outputs. Now, we have examples like that. There's nothing wrong with them. They just get a lot more complicated. So we tend to like functions because we know that if we plug in an x value, we're only going to get one answer out. So we do like functions. When we have a function, what we do is we use what's called function notation. So instead of writing the y as our variable, we'll switch to this f of x notation, which basically just tells the reader that this is a function. So it kind of just lets you know that it's an easier thing to work with, right? When you plug in a value, you're just going to get one value out. So the example that we had on the previous page, that 2.5x, is actually a function. If you think about all those different points we plugged in, we only ever got one answer out, right? You didn't get multiple answers out. So that is a function. So what we can do is we can switch the notation to look like this. And like I said, this doesn't mean that you're multiplying anything. It doesn't change the problem. It just tells the reader that this is a function. So let's practice using that function notation a little bit here. So we're told f of x. We also can use g of x, h of r, etc. So you can switch the letters or the variables, and it's still the same meaning. So a lot of times we'll use different letters for our functions to just show different equations. And you can also use different variables as well. So if you're not using x, you want to use r, it's the same idea. So if you see this kind of notation with the parentheses here, then it's function notation. So here, when we're evaluating, the number that's inside is always your x value. So we're going to just plug that right in to our x here, just like we did in the previous examples. So f of 4 just says to take that x and replace it with 4, and then we can simplify. 2 times 4 is 8. 8 plus 3 is 11. So this gives us f of 4 equals 11. Same thing here. The inside value just gives you -2. So we take our function, and anytime I see an x, I'm just going to replace it with -2. Watch your order of operations. I have to use my exponent first here. So this is -2 times -2, which is 4. 4 times 2 is 8. 8 minus 1 is 7. So I have g of -2 equals 7. And then finally here, I'm looking at h of -5. So I wrote x because I'm so used to it, but actually technically I guess we're using r here. So I'm just going to go ahead and plug in. Now, anytime I see an r, I'm going to replace it with -5. Right? And then again, I'm going to simplify first. So here I have -5 times -5 times -5. So that's -125. Minus 2, and then -5 squared is +25. So I have -125 minus 50 plus 5 here. So combining my first two, I have -175 plus 5, which is -170. So h of -5 is equal to -170. Now, each of these actually can be written in point form as well. So when you have function notation, you still have a point. This is your x value, and this is your y value. So you could still graph these using the same techniques we've been using. You just transfer to the point format. So here, this is my x value, and this is my y value. So -2, 7. And again, I know it's kind of weird because we're using r instead. So I guess technically this is your r value, but it would be like your x value on your axis. And then this would be your y value here. So it would be -5, -70. All right, let's do another example. All right, so this is an example. This is example 5 in your text if you want to read it a little bit closer up. It says, tailgaters beware. If your car is going 35 miles per hour on dry pavement, your required stopping distance is 160 feet or the width of a football field. At 65 miles per hour, the distance required is 410 feet or approximately the length of 1 1/10 football fields. Again, that's the length. The other one was the width. So figure 7.6 shows stopping distances for cars at various speeds on dry roads and on wet roads. And then figure 7.7 uses a line graph to represent the stopping distances on dry roads. So this one's just on dry. Here you have dry versus wet pavement. Okay, so here you have your speed at the bottom. So let's say a car is going 35 miles per hour. If the pavement's dry, it needs about 160 feet to stop. If the pavement's wet, it needs 185 feet to stop. And then over here, you have that same information, basically. Obviously, there's more data over here, but just kind of in a line graph form. So you're just using points instead of bars. Use the line graph in figure 7.7 to estimate the car's required stopping distance at 60 miles per hour on dry pavement and round to the nearest 10 feet. So if I'm looking at my line graph here, I'm looking at 60 miles per hour. If I just go up to this point here and go over, I can get a rough estimate about what this looks like. So it looks like it's pretty much in the middle between 300 and 400. So I would maybe guess about 350 or 360, trying to see exactly where it lines up here. Okay, so it's kind of like right in the middle. So I think 350 is a good estimate. Your book uses 360 as their estimate, so right around that kind of middle point. I'll go with your book here and say that's about 360 feet for that estimation. And again, you can see that it's pretty clearly halfway between 300 and 400. So we're just estimating there. Now, they actually have a function that models this data. So it's actually pretty common to look at stopping speeds. It's used obviously for speed limits on roads. So they can use this idea to help form different speed limits on different roads as well. So roads that are more curvy or more dangerous, you do see slower speed limits. Obviously because they just make sense, but also because of things like stopping distance to avoid accidents. And then this can also help with things like criminal justice and crime scenes, right? If cars are speeding or things like that. So there is actually a more specific function than just looking at the graph too. And it's this one right here. So this function models a car's required stopping distance in feet. Again, we're talking about on dry pavement here. Traveling at X miles per hour. Use this function to find the required stopping distance at 60 miles per hour. And again, we're going to round to the nearest right here. All right, so X is miles per hour, so X is going to be 60 in this case. We're going to go ahead and plug that in. I'm going to switch colors just so we can see a little better. So let's see, it's 0.0875, and then that X I'm going to replace with 60 minus 0.4, and again, that X I'm also going to replace with 60. So I'm just taking that function, and anytime I see an X, I'm going in and I'm replacing it with my value, which is 60 here. Now I'm going to do 60 squared first. 60 times 60 is 3,600. Now I'm going to go through and do my multiplication following order of operations. So my first value when you multiply it out, and you definitely just take out your calculator here, is 315. My second value when I multiply it out is 24. And when I add these all together, I get 357.6. Now it said to round to the nearest foot. So I want to round to the nearest whole. So because 6 is big, it's going to bump that 7 up. So I get about 358. And you can see this is obviously more accurate, right? So 360 was really close using the graph, but it was hard to see. Like I said, I probably would have said 350, so I really wasn't sure where that lined up. Either way, still a good estimation, but when we have that function formula or just an equation, we can get that better estimate here. So they're pretty close to each other in their estimations. Now we can graph functions, and I've kind of mentioned this already, the same way that we just graph our regular equations. So I've already shown you how we can take that function notation and transfer it back to point notation. So we're just going to do a little bit more practice with that. So the graph of a function is the graph of its ordered pairs, and we can graph functions just like we graph equations. So let's graph these two functions on the same rectangular coordinate system. We're going to select integers from -2 to 2, inclusive, meaning including those n values of -2 and 2 for x. So I'm going to do x, and I'm going to do my first function. I'm going to make a little table here, and then I'm going to do x, and I'm going to do my second function. And we're going to do values from -2 to 2. So -2, -1, 0, 1, and 2. All right. And I'm just going to go ahead, and anytime I see that x, I'm just going to replace it with my x value here. So it's going to be 2 times -2, which is -4. Here, 2 times -1 now, which is -2. Again, just replacing the x, 2 times 0 this time, which is 0. 2 times 1 is 2, and 2 times 2 is 4. So as a point, this would be -2 comma -4, -1 comma -2, 0, 0, 1, 2, and 2, 4. And then I'll do the same thing here. So I have 2 times -2 plus 4. So 2 times -2 is -4 plus 4 is 0. Next, I have 2 times -1 plus 4. So that's going to be -2 plus 4, which is 2. 2 times 0 plus 4. 2 times 0 is 0. So my answer is just 4. 2 times 1 plus 4. So I have 2 plus 4 is 6. And 2 times 2 plus 4, which is 4 plus 4, which is 8. So my points here are going to be -2, 0, -1, 2, 0, 4, 1, 6, and 2, 8. So you can see very little change here. I'm using that function notation, but I'm still doing the same process. If you want to, you could even switch the function notation back to y. Actually, this one should be g, so I'll fix that to be like that one there. Now we're just going to plot. So there's nothing different here. I'm going to plot my points. So let's see, I have -2, -4. Make sure I don't make any mistakes this time. -1, -2, 0, 0, 1, 2, and 2, 4. And again, I have a nice linear equation here. So you can see that my graph is just forming a straight line. All right, so this is f of x. And then for my other example, I'm at -2, 0, -1, 2, 0, 4, 1, 6, and then 2, 8. So let me see, 2, 5, 6, 7, 8. And there are my two functions graphed. So nothing new really, just working with that function notation and just kind of getting used to switching back and forth between the function notation and the regular y notation.